All right, ladies and gentlemen, today's class recording has started. Down at the bottom, there's some weirdness, but it's fine. All right, so yesterday we introduced the kinetic theory of matter. And we said that the kinetic theory of matter explains why matter exists in some certain state, either as a solid or a liquid or a gas. We could actually go take that up to plasma, but for today and tomorrow and next week, we're just going to focus on those states of matter that we are most familiar with. Okay? So, during our discussion yesterday about the kinetic theory, we said that there were two factors that determine why something exists as a solid or as a liquid or as a gas. What were the two factors that determine that? Mass and volume makes something matter. Okay, so any kind of matter, whether it's solid, liquid, or gas, makes something matter. But yesterday we talked about, okay, why does that matter exist as a solid or a liquid or a gas? One of them is temperature, because what does the temperature tell us about the particles that make up an object? Energy, and that relates to what? What they're doing, how fast they're going, right? So the speed of the particles, or the temperature, is one factor that determines the state of matter. What's the other factor that we talked about? It's a little bit harder to quantify. Motion and speed of the particles and that's our temperature, right? Okay. Will's going back to his outline from yesterday. Good, right?
Wait.
No. Okay. The attraction of the particles, right? So, how fast do they go and how much are they attracted to each other? Those are the two factors that determine whether something is a solid or a liquid or a gas. Okay? Now, today, we're going to talk about phase changes. Taking something that currently is a solid and turning it into a liquid. Or taking something that is a liquid and turning it into a gas. Or going the opposite direction. Taking something that's a gas and turning it into a liquid. Okay? That means that what are we going to have to consider? What determines the state of matter that something exists in? Temperature and attractions, right? The motion of the particles and the attractions between them. So in order to change the state of matter, we're going to have to change one or both of those factors. Okay? All right. Down here, and I don't know what, okay. All right, down here at the bottom, there is a triangle, and you have this little triangle picture on your sheet as well. It shows the three states of matter that we are most familiar with here on Earth. Remember, we talked about that plasma and bosons and condensate do exist, but the conditions necessary to make those states of matter don't exist very often here on Earth. So we're just going to stick with solid, liquid, and gas. Okay? In between the different states of matter, you'll see sort of a double-headed arrow, or kind of two arrows next to each other, implying that we can go, this is a two-way street. We can turn a solid into a liquid, but we can also turn a liquid into a solid. Because phase changes are when something changes their state of matter. They are reversible physical changes. If something is a physical change, what does that mean? We talked about that like at the end of last week. Zach, go ahead.
The properties change.
Good. Good. Like there are some property changes, but the chemical makeup, the composition of what we're dealing with hasn't changed. Okay? So there are definitely some property changes, but the chemical makeup is still exactly the same. Okay? We haven't made anything new. Now, first mention of this as our theme for the day. In order to change the state of matter of something, we're not changing its composition, but we are changing the state of matter. That involves a significant change in its energy. Okay? We are not changing what's there, but the energy of that substance will change pretty significantly. Okay? And what kind of energy change is involved and how the energy changes will determine what change of state we have. Okay? All right. Good so far? Okay. let's take a look at this double-sided arrow here at the very bottom of your triangle, the transition between solids and liquids. What do we know about the difference between particles in the solid state versus particles in the liquid state? Kareem. Good. Are they stationary? No, they are like vibrating a little bit, but they don't move very much. How much do the particles move in the liquid state? A lot more, right? Maybe not as, obviously not as much as the gas state, but they do move more. What else does that mean, right? If the particles don't move very much in the solid state, what can they do to each other? They can attract each other pretty strongly, right? And that keeps them in this nice orderly arrangement. If they move more, right, they can't attract each other as much, and that allows them to sort of move past each other, and we don't have this nice orderly arrangement that a solid has. So, let's take a look at this arrow that goes from solid to liquid. It's labeled as melting, and I think most of you probably know that. When something turns from a solid into a liquid, we say that it melts. But, if we look at the end of this arrow, what color is the end of this arrow? Red. What do we have to do energy-wise? What do we have to do energy-wise in order to turn something from a solid into a liquid? We have to increase the energy, right? We most often or most easily increase the energy by doing what to our solid? Make it hotter, right? We increase its temperature. So the arrow going from solid to liquid is red, right? But if we go the opposite way, turning something from a liquid to a solid, what do we know about the energy of the particles in the solid state compared to the liquid state? What's true about the energy of the particles in the solid state versus the liquid state? They're low, right? They have lower energy in the solid state than they do in the liquid state, right? Meaning, what do we have, or go ahead.
Okay, so is everything that's a solid naturally, like at its freezing temperature?
No, we can be below its freezing temperature and it will still be a solid. The freezing temperature is the temperature at which this transition occurs.
So technically, like everything solid that's naturally solid is freezing.
Is frozen.
Frozen.
How about that?
All right.
Yes. Technically, everything that is solid is in a frozen state. Okay? We'll talk about that temperature tomorrow. Okay? Anna, go ahead. Okay. Some substances, so wood, before it can turn into a liquid state, also wood's a mixture, so some parts of the wood have different melting points than other parts of the wood. That's the thing with a mixture too, because you have different things and they have, remember mixtures, things that make up mixtures keep their properties, right? So certain parts of a mixture might melt more easily than other parts of a mixture. But one of the things with wood is, before it gets warm enough where it can start turning into a liquid state, it actually starts going through a chemical change, and that chemical change is burning. And so we don't see that transition into the liquid state because another change occurs before that change can happen. Does that make sense? Right? So that's sort of like, that's why we don't see wood melting, because before it can turn into that liquid state, it goes through a chemical change as opposed to a physical. Okay? What's good? Okay. Such as? Okay, that might be it. That we're getting. Oh, so like, are you talking like maybe like pottery or something? Okay, yeah. In that case, as opposed to, we're not necessarily turning that liquid into a solid by heating it. We're getting the water out of it. Yeah, we're basically drying the water out of it, because clay is a mixture. One of the things that clay has in it is water. But water makes it soft and gooey, and when we don't want it to be soft and gooey anymore, we want to get rid of that water, so increasing that temperature gets rid of the water, it Okay, one more. No, pick it up. Okay.
Would caramelization be a form of melting?
Caramelization is more of a chemical change because once you take that sugar, once you caramelize it, right, it's not sugar anymore, right? It has different taste, it has different color, all those things that we talked about that indicate chemical change. You can't take caramel and turn it back into sugar, right? So that's more of a chemical change as opposed to a physical change. Okay?
Is the change in taste a chemical change?
Mostly yes, although you really shouldn't be tasting things you don't know what they are in order to determine if there's a chemical change. So, as a general rule, don't taste things to see if they've turned into something else. So, okay. All right, one more.
So going back to the sugar cane,
Yeah.
and like if you mix sugar, you can't turn sugar back to sugar.
Yeah.
And why is turning soft clay into harder clay? Or what I was trying to say was melting, and if you can't turn it back into sugar.
If you soaked it for a long time, you would probably see that some of that clay stuff would start dissolving back into the water. So yeah, you're just getting rid of that water. You're not really making something new with that point. All right, so let's talk about these energy changes. Sometimes we have to increase the energy of those particles by increasing the temperature. Sometimes we have to decrease the energy of those particles. Whether we have to increase or decrease the energy determines what happen or what we call this type of process. What do we know about energy in general? What did we learn in our last unit about energy total? I know that was kind of a broad question, but what's true about the amount of energy in a system? Energy is not created or destroyed. What do we call that concept? Conservation, right? Energy is conserved. So, if we have to, let's say, an ice cube, if we want to turn that ice cube from a solid ice cube into liquid water, what do we have to do to the energy of those particles? We have to increase the energy of the particles, right? Well, if the energy of those particles is increasing, what else has to be happening somewhere? If the energy of those water molecules is increasing, what else has to be happening? Something else has to be decreasing. Because what has to be true about the total amount of energy? It has to stay the same, right? If you hold an ice cube in your hand, and that ice cube goes from a solid to a liquid, those particles are increasing in energy. Where are they getting that energy from? From your hand, right? What happens to your hand as the ice cube melts in it? It gets colder. Why? Because the energy is flowing out of you and into the ice cube. Okay? So when we have these changes of state, energy either flows into our substance, but sometimes it'll come out of our substance. Right? Depending on whether energy flows into it or out of it, we classify those changes as endothermic or exothermic. Right? So B, letter B in your outline. Endothermic. Energy can go into a substance. But then, letter C down at the bottom, where it says exothermic, right? Something is exothermic if we release energy from that substance into our surroundings. And so letter B in your outline, where it says endothermic, right? Energy goes into the substance. But, in letter C, exothermic energy is released to the surroundings from our substance. Okay? Good with those terms for starters. Okay? All right, let's talk about one phase change that you are all probably pretty familiar with, melting. Okay? Melting is the transition from what state of matter to what state of matter? Solid to liquid, right? Okay? And as we just discussed, so let's talk about the particles as they go from solid to liquid, right? Okay. Just number one, melting. Okay. As they go from solid to a liquid, what happens to the particles first? They speed up, right? They increase in energy. What else will They spread apart because as they move faster, what can they not do to each other quite as much anymore? Attract each other, right? So as something goes from solid to a liquid, the speed of the particles increases. That causes the attractions to become weaker, and that allows those particles to move around a little bit more. All right? Particles become less ordered. The molecules vibrate more and more and more, and they finally get enough energy so that they sort of break out of that nice rigid arrangement that they have when they are a solid. So, did our particles have to gain energy or lose energy in order to do this? They have to gain energy. If the particles, if the substance is gaining energy, energy is flowing into it, and so that makes this what kind of a process? Endothermic or exothermic? This is an endothermic process, okay? We have increased the energy of those particles, okay? Good.
So let's say you're running.
Yep.
And you heat up.
Good.
Is that considered endothermic energy?
So, okay, you running involves a chemical reaction in your muscles to make your muscles move, okay? That chemical reaction overall is an exothermic process. It releases energy, okay? So what does that do then to your body temperature? It raises your body temperature, but then what do you do with that heat that has been left over from your muscles working? You sweat to try and get rid of that heat, right? Or your face turns all red and you get, like if you get close to somebody, they feel warm, right? Because your body is trying to get rid of that process. So that is an exothermic process because we're releasing that energy that's left over from our muscles doing that work. Okay? All right. What other phase changes would be endothermic? What other phase changes would require us to increase the energy of the particles? You can talk about it just in terms of states of matter, going from what to what.
Vaporization.
Vaporization is the transition from what to what?
Liquid to gas.
Okay, if we want to turn something from a liquid into a gas, what do we have to do to the energy of the particles? Increase the energy of particles. That means we have to put energy into it. That means it's an endothermic process, right? So let me go here, and let me go here, okay? So to finish off this section, right? Vaporization is what we call the transition from liquid to gas. It is also an endothermic process because we have to increase the energy, okay? Let's go ahead. Okay, 1C. Oh, the particles are no longer in their fixed arrangement or orderly arrangement, if you want to talk about that, right? The nice, like we said, particles in particles that make up a solid are in a nice orderly arrangement, right? Okay? So if we go from that solid to liquid, now they're not in that orderly arrangement anymore. Okay? All right. So vaporization is another endothermic process. We have to increase the energy of the particles. What other change could we talk about?
Sublimation.
Sublimation. If you look up your triangle up at the top of the page. Sublimation is the transition of particles in a solid directly to the gas phase. It doesn't happen too often, but it does happen. You guys are probably familiar with one really like famous example of sublimation. Do you know of any substance that goes straight from a solid phase into a gas phase? This dry ice, right? Dry ice goes directly from a solid into a gas phase. If you put dry ice on the counter, let it go, it won't end up as a puddle, right? It ends up as a gas. It just goes out into the ring. It is no. Okay? It it's heating up, but it feels cold because if you put it in your hand, where is it getting its energy from? From your hand. That's why it feels cold. But it's warming up. It just has to get the energy from somewhere. Like, even if you don't touch it, if you just put your hands next to it, it feels cold. Because if your hand isn't touching it, where is it getting its energy from? From the air that surrounds it. And that makes that air feel colder because it's losing energy. Okay? Anna, go ahead.
Why does it stick to
A
the
lot of it has to do with the molecular structure, how the atoms are put together. We will look at that a little bit later on in the year. Just carbon dioxide, dry ice is carbon dioxide, just like carbon dioxide that you breathe out when you exhale. It's a pretty simple molecule, and it's all like very straight. Carbon's in the middle, and oxygen is right on the sides. And so it doesn't allow for a lot of attractions between those particles. Most of the time, you think of carbon dioxide in what state of matter? Gas, right? Because there aren't a lot of attractions between those CO2s and other CO2s. But if it's cold enough, the way that they line up, they'll go directly into that solid phase. Not a lot of things do that, but some materials do. Okay? And we'll see tomorrow that it's not just a temperature thing, it's also a pressure thing. And we'll talk about that too. Kind of good. Anybody?
Or not, like, the C is in, no. Oh, is it there's
Okay, good there? Oh, sorry. Sublimation is what we call that solid to gas transition. Sublimation. All right, good there? Oh, too far. Okay, let's talk about this transition. Let's talk about freezing. Freezing is when something goes from one state of matter to what state of matter?
liquid to solid?
Liquid to solid. If something's going to go from a liquid to a solid phase, what has to happen to the energy of those particles?
It has to slow down.
They have to slow down, right? The energy has to decrease. If those particles slow down, they don't move as fast, right? What can they start doing to each other more? They can start attracting each other more. They can start holding on to each other more. And when they do, that transitions them into a solid phase. So as something freezes, right? So number one is going to be freezing. The energy of the particles decreases. They move more slowly. And that means they start holding on to each other more often, right? They start increasing the attractions between them. Okay? The average energy decreases. Particles move more slowly. And because they move more slowly, right, they start to hold on to each other more. And they don't have as much freedom of motion. If they don't have as much freedom of motion, now they transition into that solid phase, right? That nice orderly arrangement where they're sort of holding on to each other. Not sort of, but they're holding on to each other. All right, from an energy standpoint, what has happened to the energy of these particles? They have slowed down. That means their energy has decreased. But because of conservation, if the energy of one thing is decreasing, what else has to be happening? Something has to be increasing, right? So those are back like before, right? In this case here, as those particles freeze, they actually release energy into the air around them. Generally speaking, as far as you're concerned, this process of freezing happens where most often? In your freezer, right? So, as liquid water turns into solid water, what actually happens to the temperature inside of your freezer? It actually goes up a little bit. If that continued to happen, your freezer wouldn't stay cold. So what does the motor on your freezer do? It gets rid of that warm air and replaces it with more cold air to keep the temperature low, or hopefully cold. If the power goes out, what are you not supposed to do? Open the freezer. Because what?
Coldness will get out and then it won't get replaced.
Actually, coldness doesn't get out.
Warmness goes in.
Okay? Because we have that change in temperature, right? So the warmness, the quote-unquote warmness, represents what? Energy, right? Coldness is just a low amount of energy, right? So warmness would actually go into your freezer, right? Your freezer works hard to continually remove the energy that substances release as they freeze. Okay? That makes freezing itself an exothermic process because it releases energy. What other transitions are going to be exothermic processes? What other states of matter transition do we need to decrease the energy of the particle? Yeah. Deposition and condensation. Most of you are probably more familiar with condensation. That's the process of turning a gas into a liquid. In the morning, when your grass is dewy, right? What has happened to the water vapor in the air? It is condensed. It has turned into a liquid. Because of that, what's actually true about the air temperature in your front yard? A little bit. It goes up a little bit. When it's really dewy and foggy in the morning, it's usually not very cold. Because as all that water transitions from gas phase into liquid phase, it releases some energy, right? So this condensation, gas to liquid, is also an exothermic change. And go ahead.
Last year, we learned about like rocks and stuff.
Yep.
And we talked about deposition in that context.
Okay.
What's the difference?
Okay, so deposition. Okay, did everybody hear Hannah's question or no? She said last year you guys did kind of some geology stuff, and you talked about rocks and like deposition of like sediment and stuff like that. Okay, so let's talk about why this is also deposition. Deposition is the transition of a gas straight to a solid. Okay? You guys are most familiar with this in the winter time when it gets really, really cold. If you wake up in the morning and there's frost on the window, little ice crystals, right? That's solid water. That solid water came from the water vapor that's in the air. But if you watched it all night, you wouldn't see little water droplets form first, and then those water droplets turn into solid. It goes straight from the gas phase into the solid phase. Okay? So, back to why is it deposition? Deposition is kind of the process of something sort of settling, right? Deposition is like when sediment just kind of like keeps piling up, right? Am I right on that or no? Is that, like deposition is like,
And like deposits on the bottom.
yeah, like a riverbed or something like that, right? Okay. That's what's happening here, is that liquid is just sort of settling, or sorry, not the liquid, the gas, water vapor settles into the solid phase, and that's why it's deposition. Okay? But, most importantly, to wrap this up, right, that process releases energy. because the particles in the solid phase have less energy than the particles in the gas phase. Okay? All right. If you look at the calendar real quick, you'll see here on Thursday, there's a section of your book, section 3.3, that's about phase changes. It's page 84 to page 91. If we haven't done all of this yet, we will talk about heating curves tomorrow, but it does talk about the different phase changes and whether they're endothermic or exothermic. So if you want to review that a little bit tonight, it might be a good idea. Yes, Kareem? Yeah, the quiz is due tomorrow evening, but it does the quiz that's due tomorrow doesn't cover any of the phase change stuff. It's just mixtures, pure substances, kinetic theory, solids, liquids, gases. At 11:59, yes. So set your alarm. Yeah. All right, everybody, good job today. We'll pick this up tomorrow.